Three-phase power systems form the foundation of modern electrical power generation, transmission, distribution, and utilization. The choice between star Y and delta connections is one of the fundamental concepts that determines how electrical energy is generated, transmitted, distributed, and consumed. A three-phase system consists of three alternating voltages or currents that are displaced from one another by 120 electrical degrees. This phase displacement allows three-phase systems to deliver electrical power more smoothly and efficiently than single-phase systems. As a result, three-phase systems are widely used in industrial facilities, commercial buildings, electrical distribution networks, large motors, and interconnected power systems. The 120-degree relationship between the phases also provides an important electrical advantage because, in a balanced system, the vector sum of the three-phase currents is zero. This characteristic reduces the requirement for a separate return conductor and allows electrical power to be transmitted efficiently using 3 or 4 conductors. The reduction in conductor requirements becomes particularly important in high-voltage transmission systems where transmission lines may extend over hundreds of kilometers. The behavior of a three-phase system can be understood through the geometric relationship between its phase voltages and currents. The three electrical quantities can be represented as phasors separated by exactly 120 degrees, forming a symmetrical arrangement. Under balanced operating conditions, the three-phase quantities have equal magnitudes and their vector sum is zero. This property allows the system to provide relatively constant instantaneous power to balance loads. Unlike a single-phase system, where instantaneous power continuously rises and falls during each electrical cycle, a balanced three-phase system provides a much smoother power transfer. This characteristic is especially important for large industrial motors because it reduces torque pulsations, mechanical vibration, and mechanical stress. It also contributes to reliable operation of industrial processes and electrical equipment. The selection of 120 degrees as the phase displacement therefore provides the mathematical and physical foundation for the efficiency and practicality of three-phase electrical systems. The star connection, also known as the Y connection, is formed by connecting one end of each of the three-phase windings to a common point known as the neutral point or star point. This arrangement provides considerable flexibility because a neutral conductor can be connected to the common point. As a result, the same electrical system can supply both three-phase line-to-line loads and single-phase line-to-neutral loads. This capability makes star-connected systems particularly suitable for electrical distribution networks supplying residential, commercial, and mixed industrial loads. The most important voltage relationship in a balanced star-connected system is that the line voltage is equal to the phase voltage multiplied by the square root of 3, which is approximately 1.732. Conversely, the phase voltage is equal to the line voltage divided by the square root of 3. The current relationship is simpler because the line current is equal to the phase current. These relationships explain why a star-connected distribution system can provide two useful voltage levels from the same electrical infrastructure. For example, a 400-volt line-to-line system provides approximately 230 volts between phase and neutral. This allows three-phase motors and other industrial equipment to operate at the higher line voltage while lighting, computers, receptacles, and other single-phase equipment can operate at the lower line to neutral voltage. The neutral conductor represents one of the most important characteristics of the star connection. In a perfectly balanced three-phase system, the three-phase currents cancel each other at the neutral point because they are separated by 120 degrees. Consequently, the neutral current is theoretically zero under perfectly balanced conditions. In practical electrical systems, however, loads are rarely completely balanced. Commercial and industrial facilities contain different combinations of lighting, heating, air conditioning, motors, electronic equipment, and other loads that change continuously. Therefore, the neutral conductor can carry significant current during normal operation. An additional concern is the presence of nonlinear loads such as variable frequency drives, switched-mode power supplies, rectifiers, and electronic converters. These loads generate harmonic currents, including triplen harmonics such as the 3rd, 9th, and 15th harmonics. Unlike the fundamental current components, triplen harmonic currents can add together in the neutral conductor instead of canceling. This can result in considerable neutral current and may produce excessive heating if the conductor is not correctly sized. Proper harmonic assessment and appropriate conductor selection are therefore important aspects of star-connected distribution system design. The star connection also provides important grounding and protection benefits. The neutral or star point can be connected to Earth through a solid connection or through an impedance. Grounding the neutral establishes a stable voltage reference for the electrical system and provides a predictable path for fault current when a phase conductor comes into contact with grounded equipment or earth. The resulting fault current can be detected by protective relays, circuit breakers, fuses, and ground fault protection systems. The protection equipment can then isolate the faulty section of the network, reducing the possibility of equipment damage, fire, and personnel hazards. Solidly grounded star systems are widely used because they provide effective fault detection and straightforward protection coordination. Other grounding arrangements include resistance-grounded star systems and ungrounded systems. Resistance grounding limits the magnitude of ground fault current and can reduce equipment damage, while ungrounded systems may allow continued operation following an initial ground fault but can result in increased voltage stress on the unfaulted phases. The grounding method must therefore be selected according to system voltage, equipment characteristics, fault levels, protection requirements, and operational objectives. The delta connection has a different physical and electrical arrangement. In a delta configuration, the three windings are connected end-to-end to form a closed triangular loop. There is no common neutral point in the conventional delta arrangement, and the external system normally uses three conductors. The electrical relationships in delta are essentially the reverse of those in star. Each phase winding is directly connected across a line-to-line voltage, meaning that the phase voltage is equal to the line voltage. However, the line current is equal to the phase current multiplied by the square root of 3. These characteristics make delta connections particularly suitable for heavy industrial applications and three-phase motors. Because every winding receives the full line voltage, the power consumed by identical impedances connected in delta is greater than the power consumed when those same impedances are connected in star at the same supply voltage. For identical balanced impedances, the delta configuration consumes 3 times the power of the corresponding star configuration. This relationship is important in the design and operation of motor circuits, industrial heating systems, and transformer applications. An important technical advantage of the delta connection is its ability to provide a circulating path for triplen harmonic currents. Nonlinear electrical loads can generate third, ninth, 15th, and other triplen harmonic currents. In a star-connected system, these currents can accumulate in the neutral conductor. In a delta winding, the closed triangular path allows these harmonic currents to circulate within the winding rather than being transferred directly into the external network. This characteristic can help reduce harmonic propagation and improve power quality in the connected system. Delta-connected transformer windings are therefore commonly used in applications involving variable frequency drives, rectifiers, arc furnaces, and other nonlinear loads. Although a delta winding provides useful harmonic containment, it should still be supported by appropriate harmonic studies and additional filtering when harmonic distortion is significant. Grounding behavior represents another important difference between star and delta systems. A conventional delta system does not have an inherent neutral point, so grounding must be provided through an appropriate system arrangement when grounding is required. Historically, ungrounded delta systems were used in industrial applications where continuous operation was particularly important. Since an ungrounded system does not provide a direct low-impedance path for ground fault current, an initial line-to-ground fault may produce relatively limited current and allow the system to continue operating temporarily. This characteristic was useful in continuous process industries where an unexpected shutdown could cause substantial operational and economic consequences. However, ungrounded systems also create important risks. During a sustained ground fault, the voltage of the two unfaulted phases relative to ground can increase significantly. This increased voltage can place additional stress on equipment insulation and increase the probability of another fault occurring. A second ground fault can then develop into a much more severe phase-to-phase fault. Modern practice therefore frequently uses controlled grounding methods such as high-resistance grounding, which limits fault current while allowing protection and monitoring systems to identify the fault and support corrective action. The difference between star and delta connections is also applied extensively in induction motor starting. Large induction motors can draw several times the rated full load current when they are started directly across the supply. This high starting current can produce voltage dips in the electrical network and may affect other connected equipment. A star-delta starter reduces this impact by initially connecting the motor windings in star. Each motor winding then receives approximately 57.7% of the line voltage because the phase voltage is equal to the line voltage divided by the square root of 3. Since starting current is approximately proportional to the applied voltage, the supply starting current is significantly reduced. However, starting torque is also reduced and becomes approximately 1/3 of the torque available during direct delta starting under comparable conditions. Once the motor reaches sufficient speed, the starter changes the winding configuration from star to delta. Full line voltage is then applied to the motor windings, allowing the motor to develop its normal operating torque and continue running under rated conditions. This method provides a relatively simple and economical method of reducing motor starting current and voltage disturbance, although it may not be suitable for loads requiring high starting torque. Star and delta connections are also fundamental to transformer design and system integration. Power transformers frequently use different winding configurations on their primary and secondary sides to combine the advantages of both arrangements. A delta winding can provide a closed path for triplen harmonic currents, while a star winding can provide a neutral point for grounding and for supplying line to neutral loads. A common transformer arrangement therefore uses a delta-connected high-voltage winding and a star-connected low-voltage winding. This arrangement allows the transformer to receive three-phase power through the delta winding while providing a grounded neutral and both line-to-line and line-to-neutral voltages on the secondary side. Transformer vector groups describe the phase displacement between the primary and secondary windings and are critical when transformers are connected in parallel or integrated into larger power networks. Incorrect vector group selection can produce phase displacement errors, circulating currents, excessive loading, and incorrect operation of protection systems. The selection between star and delta should therefore not be considered as a simple decision about which configuration is better. Each connection provides specific technical characteristics that make it suitable for particular applications. Star is particularly useful when a neutral point, grounding reference, and multiple voltage levels are required. This makes it highly suitable for distribution systems serving a combination of three-phase and single-phase loads. Delta is particularly useful when full line voltage must be applied across phase windings, when heavy industrial loads are involved, and when harmonic containment is beneficial. The economic comparison should also consider the complete electrical system rather than simply comparing the number of conductors. Although a star system may require a neutral conductor, the ability to supply both line-to-line and line-to-neutral loads from the same infrastructure can eliminate the requirement for separate transformers or distribution arrangements. Delta systems can reduce conductor requirements and provide other operational advantages, but their lack of an inherent neutral point limits their suitability for certain types of loads. From an operational and maintenance perspective, engineers and technicians must understand the connection arrangement, grounding method, phase relationships, transformer vector group, and protection philosophy associated with each electrical system. Ground fault protection settings can differ significantly depending on whether the system is solidly grounded star, resistance grounded star, or delta. Phase rotation and transformer phase displacement must also be verified before equipment is energized or transformers are operated in parallel. Maintenance activities must take into account the possible fault current paths, neutral arrangements, grounding connections, and transformer configuration. These considerations become increasingly important as modern power systems incorporate variable frequency drives, renewable energy converters, battery systems, electric vehicle chargers, data centers, and other power electronic equipment. Such equipment can introduce harmonic currents, unusual load characteristics, electromagnetic interference, and other power quality challenges that must be considered during system design and operation. Modern electrical networks are continuously changing because of increasing electrification, renewable energy integration, inverter-based resources, electric vehicle charging, and the rapid growth of power electronic loads. These developments create new challenges for grounding, harmonic management, fault current behavior, protection coordination, and power quality. At the same time, the fundamental principles of star and delta connections remain unchanged. Engineers continue to use these configurations because their electrical characteristics provide practical solutions to different system requirements. Advanced transformer arrangements, harmonic mitigation equipment, grounding transformers, zigzag transformers, active filters, and sophisticated protection systems can be used to address situations where the advantages of star and delta must be combined or where their limitations need to be managed. Ultimately, star and delta connections should be considered complementary engineering configurations rather than competing technologies. The star connection provides a neutral reference, grounding flexibility, and the ability to supply both line-to-line and line-to-neutral loads, making it particularly valuable in electrical distribution systems. The delta connection provides full line voltage across each phase winding, does not require an inherent neutral conductor, and provides a closed path for triplen harmonic currents, making it particularly useful in industrial applications and transformer systems. Modern transformers frequently combine both configurations because their characteristics complement one another. A proper understanding of star and delta connections is therefore essential for electrical engineers involved in power system planning, transformer design, protection coordination, motor applications, grounding studies, power quality assessment, operation, and maintenance. As electrical networks become increasingly renewable, distributed, electronically controlled, and interconnected, these fundamental connection schemes will continue to play an important role in maintaining safe, reliable, efficient, and economical power systems.